We're going to revisit our bank salaries data set, and we can see from this side-by-side box plot here, we are looking at salary. So these are annual salaries, but the data are from the 60s and 70s. So these are kind of Mad Men money, right? So 1960s. They look kind of like monthly salaries, but they're actually annual salaries. And this is broken apart by gender, which is categorical. Salaries, of course, would be my quantitative variable. In this data set, we will address the question of whether starting salaries in the banking industry are higher for males than for females, or were at least in the 1960s and 1970s. So let's start by getting this data set loaded into StatKey. We're going to go to test for difference in means. Remember that when we have one categorical and one quantitative variable, a difference in means is a statistic that we can look at to summarize it. This will be under the heading of randomization hypothesis tests, just like the tests we've done earlier in this lesson. So here in StatKey, I'm going to test for difference in means under randomization hypothesis tests, and I'm going to upload this file, which you may have had to download first. This is not in the logbook, so I don't look in the datasets from logbook folder, but I'm going to pull it from this shorter list of datasets of mine. And banksalaries.csv is the correct one. I'm going to select salaries as my quantitative variable and gender as my categorical variable. And the display that StatKey gives us in this particular window is side-by-side side-by-side dot plots instead of side-by-side box plots. But we can also see this trend of a distribution that's primarily to the right for males from the distribution for females here. I think the side-by-side box plots are a little bit easier to read, even though they contain slightly less information. We can see here that it does look like the center 50% of salaries for males was entirely above, or almost entirely above, the center 50% of salaries for females. So it does look like the data support the suggestion that salaries were higher for males than for females. Coming back to our StatKey page, one of the things we need to pay close attention to with a difference of means is what order they are subtracted in. So here I can see that my x1 bar minus x2 bar in the original sample is a positive number, 818. I have to figure out which is sample 1 and which is sample 2 by looking at these two samples and seeing what their means are. I can see that the mean for females is 5138 point something. The mean for males is 5956 point something. It's higher, and therefore if I'm getting a positive value, this must be the mean salary for males minus the mean salary for females. So the first thing I need to do is just figure out what my dot plot is going to represent and which is sample 1 and which is sample 2. The designation is somewhat arbitrary, because what StatKey actually does is it starts looking through the data, and whichever gender it comes across first ends up being its first sample. So there's no way to predict in advance unless you've looked at the data set or just come to this page and seen what the actual numbers are. So what we have determined is that it is giving us x1 bar minus x2 bar, where 1 is male and 2 is female. So that means that my mu1 is the mean starting salary for all males in the banking industry. we'll at least establish that it's the mean starting salary for all males. And we'll figure the banking industry and the 60s are implied by the context. And mu2 is the same, I'll use ditto marks here, except for all females. But we do need to make sure we know which set is number 1 and which set is number 2 before we get to this stage. Otherwise it gets very confusing trying to figure out whether we want a right tail or a left tail. So our hypotheses, our null hypothesis, is that mu1 is equal to mu2. That would be the hypothesis of no difference in starting salaries. And note that this could also be written as mu1 minus mu2 equals 0. My alternative hypothesis is that starting salaries are higher for males, so again I have to refer to which subscript refers to males. That's number 1, so that's going to be mu sub 1 is greater than mu sub 2. And I could also write this as mu sub 1 minus mu sub 2 is greater than 0. The reason we have two ways of writing these, for one thing, this first form is a little bit more intuitive. It's also what Wiley Plus is going to be looking for when it asks you to write hypotheses symbolically through their template. This form over here is more useful for making sense of the randomization distribution. Because remember, our randomization distribution is for a difference of means. So each dot in that randomization distribution is a value of x1 bar minus x2 bar, which is used to estimate mu1 minus mu2. So thinking about your hypotheses in this form makes it easier to tell whether you want a right tail or a left tail. If it's still greater than 0, even when you have it written in this order, then it is going to be a right tail test. But this is why it's so important for us to get the order consistent with what we see in the graph. If set 2 had been our males and we were still writing this in terms of mu1 minus mu2, then we would have to have a left tail test. Because in that case, if males had a higher starting salary, this alternative hypothesis would actually be less than 0. So we really do have to be careful about which set is which as we're setting up and as we're stating our hypotheses. Okay, so let's go ahead and return to our stat key page here. We're going to check the null hypothesis on that page, and we're going to generate a few thousand samples and check the, oops, it says two tail box here. That should actually say right tail box, because we have a one-sided as we have identified. We will check the right tail box and try to find our p-value. Note that the null hypothesis is that mu1 is equal to mu2. Just like with correlation, we can't change this one. There's never a null hypothesis that suggests that these differ by a specific amount. It's always that they are the same as each other. So that makes it a little easier. We always have the same null hypothesis when we're comparing two means. Generating a couple of thousand samples, we get a nice looking graph here, and I'm going to select right tail. And remember that this number down here, which for me says 306.332, this is the one that I'm going to overwrite with our sample statistic, 818.02. So that's my x1 bar minus x2 bar. And we can see that it's way off to the right, kind of like our tip amount versus bill example, and that we have a small p-value of 0 to 3 decimal places. Note that we never just say the p-value is 0, because it never is truly 0. What we're interested in is that it's still 0 to 3 decimal places. So I'm going to say that the p-value is equal to 0.0000, and then we know that any non-zero digits that may come up later are further out, right? This is a very small p-value, which means that we have very strong evidence against the null hypothesis. Not a really big surprise considering what our box plot looks like and what our side-by-side dot plots here look like. So when we state the conclusion of this test, first we do a quick check to see if we were given a significance level. We were not given any value for alpha. So rather than saying we have statistical significance or we don't really go straight into a reject, fail to reject kind of situation here. Instead, we're just going to describe the strength of our evidence. A p-value this small, we would probably use the word overwhelming, or if you said very strong evidence, that would also be accurate. Now, it's a good habit to also include a little bit more detail, which is of those 3 commonly used values of alpha. Remember, the 3 commonly used values are 0.01, 0.05, and 0.1, or 0.10 if you want to take them all out to 2 digits. Of these 3 commonly used values of alpha, what's the smallest one at which we would reject? Well, we would reject at all of them, so I'm going to choose this smallest one and say, in parentheses, statistically significant at the 0.01 level, meaning that we would reject the null hypothesis at the 0.01 level, that starting salaries in the banking industry in the 1960s were higher for males than for females. So the statistical significance part of this isn't absolutely required, but it's a good habit to get into so that you're still thinking about the meaning of reject and fail to reject and statistical significance levels, and you're still getting practice with those ideas as you write your conclusions. And so just to make sure we really are getting practice with reject, fail to reject, this statistical significance at the 0.01 level does mean reject the null hypothesis at alpha equals 0.01. However, this description down here is super technical. This is a technical answer, a formal statistical decision. This doesn't really belong in your conclusion. If it's in there and your conclusion still explains things well, then it's fine. But I always ask for non-technical language to make sure that you can state your conclusion in a way that illustrates that you know what we have actually found from this in sort of plain human speak. So your conclusion should generally make sense to somebody who doesn't know any statistics at all.